In this experiment, we're going to determine the percent composition of chemicals in limestone. Goals. In this lab, we're going to determine the percent composition of calcium carbonate in limestone. We're also going to learn how to write the introduction section of our lab report. Background. Limestone is extremely common sedimentary rock that comprises mostly of exposed rock on Earth's surface. From a chemical standpoint, limestone is composed of the minerals calcite or calcium carbonate, chert known as silica or SiO2, and dolomite and calcium magnesium carbonate. In this lab, we're going to determine the percent composition of calcium carbonate in a limestone sample. To do this, we're going to first determine the amount of anion or carbonate in the sample by reacting the limestone with hydrochloric acid. Then we're going to react the remaining sample with another substance to determine the amount of calcium cation present. So how are we going to determine the percent composition of the anion and the cation? Well, we will isolate them starting with the anion carbonate. Calcium carbonate will react with hydrochloric acid, releasing carbonic acid into solution. The carbonic acid rapidly decomposes into water and releases carbon dioxide gas. We can see the gas released in the form of bubbles in the solution. This two-step process occurs rapidly and is generally described using the net reaction. Solid calcium carbonate reacts with 2 moles of hydrochloric acid solution to form aqueous calcium chloride, carbon dioxide gas, and water. We can measure the amount of limestone sample in hydrochloric acid solution. We start with run the reaction, and measure the mass of the remaining solution. Any mass difference is due to the release of carbon dioxide gas. So, working backward through the stoichiometry, we can determine the amount of carbonate present in our original sample. The cation. So we went through all of these steps to release carbon dioxide to back calculate to the amount of carbonate. However, we also have calcium now in solution as part of calcium chloride, which we need to get into a solid form to be able to measure its mass. In this case, we'll further react our solution with ammonium sulfate to form a solid calcium sulfate under basic conditions. This means the pH of the solution must be between 7 and 14 units. Adjusting the pH will change the solubility of our product, allowing it to form a solid. Calcium sulfate is a solid in basic aqueous conditions, and the other product, ammonium chloride, remains dissolved in water. This allows us to filter the solid out of the solution using a Buchner funnel and vacuum filtration to collect the solid in order to dry and determine its weight. Precipitating reagent. The ammonium sulfate we used is a substance known as a precipitating agent, meaning it selectively combines with the element of interest to form an insoluble solid in solution. Chemists can isolate the precipitate using gravimetric analysis to determine how much of the precipitate is present. Percent composition. Percent composition is the percent by mass of a component within a compound. For example, if you have a compound made of 2 components of equal mass, then the percent composition would be 50%. Let's look at an example. What is the percent composition of nitrogen in urea? CONH2, 2. We first have to find the molecular weight of urea. We know carbon's molecular weight is 12.01, oxygen's is 15.99, hydrogen's is around 1.01, and nitrogen's is around 14. We need to add all of these together with respect to their stoichiometric amounts. 12.01 plus 16.00 plus 1.01 times 4 plus 14.01 times 2 is 60.06. Now we need to determine how much of this is due to nitrogen. To do this, we take nitrogen's molecular weight, 14.00 grams per mole, and multiply it by 2 because there are 2 moles of nitrogen in 1 mole of urea. We now have 28.002, and we will divide this by 60.016 to get our percent composition, around 46.66%. Experimental techniques. pH indicators. This lab will also be your first time working with pH and indicators. pH measures how acidic or basic a solution is. A pH greater than 7 means the solution is basic, and less than 7 indicates the solution is acidic. We use pH indicators to give us an idea of what pH solutions are, therefore telling us how acidic or basic solutions can be. pH indicators come in many types, such as pH strips, like on the right, which can change color once they touch the solution, or chemical pH indicators, which change color to allow us to visually determine the pH. Methyl red is an example of an indicator that changes colors at a particular pH. If you look at the chart on the left, you can see a general idea of the color and how it changes from hot pink at a more acidic pH to more yellow color at a basic or higher pH. The ideal spot is an orange color in the middle, around pH 4 to 6, which is where the equivalent point lies. Don't worry, you don't need to memorize the information in this table. However, you will need to be able to interpret the information provided to determine what would be a good indicator to use in a different situation. Carefully read through the procedure to identify the indicator that we will use in this experiment and the color it starts out as and changes to, keeping in mind that you'll see 3 different colors as the pH changes. Gravimetric analysis. Earlier, we talked briefly about having to isolate the cation in limestone by using a precipitating agent. Well, a problem with using a precipitating agent is that while you are now have a solid at the bottom of the flask, you need to remove that solid from the liquid portion. The technique of isolating a particular component of a solution by reacting the component of interest with another substance to form a solid and filtering the solid out is known as gravimetric analysis. We're going to use both of the common methods to filter our solution: gravimetric filtration and vacuum filtration. Gravity filtration. In order to isolate the calcium cation from limestone, you need to filter any undissolved solids from the anion portion of the experiment. In our case, we're taking calcium chloride that is soluble in solution and reacting it with ammonium sulfate to form a solid. We adjust the pH a bit to make the solution basic, and the calcium sulfate will form a solid and precipitate out of solution. Gravimetric filtration simply uses gravity to push a liquid through filter paper. Often the filter paper is folded up and put into a funnel so the liquid can be collected separately of the solid. The second method we'll use is vacuum filtration. Like the name implies, we will use a vacuum to suck air out of our liquid through filter paper and a specialized funnel called a Buchner funnel before it's collected in a vacuum flask, which is a special side arm that can be attached to a vacuum source. Experimental notes. Reminders. This is a long lab that will take the full laboratory period. Your TA will briefly talk about a timeline for the lab to help you manage time and know where about you should be in the procedures so you can finish on time. We'll be conducting this experiment on 2 different limestone samples to see how they compare. Because of the length of the experiment, you need to test both samples at the same time. You cannot complete the lab with one sample and then go back and complete it with the second sample. There simply isn't enough time. When you can, find places where you can work on other tasks while we are waiting on the reaction. If you have a 15-minute wait, read the steps ahead and prepare by collecting supplies, solutions, or weights. A great point to multitask is anytime you use filter paper. Don't forget, for the last steps, you'll need to record the mass of the filter paper and watch glass, so that when you weigh the filter paper and the watch glass with your sample, you can subtract out those 2 values so you know what the mass of your sample was. You'll need to do this way in advance of putting the sample into the oven. Make sure that you let your sample dry completely in the oven before you take the mass of it. If your sample is wet, it will be heavier than you expect and will result in your ending mass being greater than your starting mass, which is not physically possible, and also makes it more challenging to write your lab report. A few reminders for this experiment. This is the first lab experiment where we'll be working with hazardous chemicals that could cause you physical harm, so we expect that you'll follow laboratory safety rules. If the hydrochloric acid comes in contact with your skin, it will cause burns, so you're expected to wear your scrubs, goggles, and gloves at all times. If your goggles fog up, please step out into the hallway and wipe them off. Do not take your goggles off in the lab room. Second, get in the habit of writing down the actual masses and volumes used. Don't spend a lot of time trying to get measurements that are exactly what's shown in the lab manual. Instead, get within the range provided and write down precisely what you used. Remember, for liquids, you should always estimate 1 decimal place beyond the markings of the glassware. Third, use distilled water to avoid introducing additional impurities into your reaction. Please make sure you follow your TA's direction on using the DI water tap and that you carefully push the handle downward when attempting to get the water on. The DI water tap is regulated, so please don't force the handle while trying to increase the rate of the water flowing out. And finally, don't forget that you need to return your glassware clean and dry to your lab drawer. Waste disposal. This experiment is the first experiment we'll be using hazardous chemicals. The substance we are using must be disposed of in a particular manner following local and federal regulations. Your TA will instruct you on the specifics as waste disposal during the lab period. For the general chemistry labs, most of what we use are acids and bases in aqueous solutions, so we generally refer to the aqueous waste containers as the waste container. Other labs will have to separate out the types of waste into separate waste containers, so please be sure to pay attention to your instructors. For this lab, make sure that you put waste in the appropriate container. Any extra hydrochloric acid, aqueous ammonia, ammonium sulfate, and methyl red go into the waste container. Please keep in mind that these should be very small quantities as you want to take close to the amount that you need. Any solid waste, like leftover limestone or other solids, can go in the trash can. When pouring waste in the waste containers in the hood, please double check before you pour your waste in the waste container that the funnel is open or in the up position as shown on the left and not closed as shown on the right. When multiple students pour waste into the closed lid of the funnel, it becomes not only a safety hazard for others in the lab, but also a serious safety hazard that is a resultant injury of our personnel preparing your labs. If you have any questions, please reach out to your teaching assistant, speak with the TA in the General Chemistry Learning Center in Jacobs Science Building, room 219, or send me an email.